Hello everyone. Today our primary focus will be to thoroughly explore and discuss the ARFIMA model in depth, and then consistent with our usual approach, we will proceed to demonstrate its practical application by leveraging the valuable resources found on the Finance Research Gate website. Alright, let's get started. The ARFIMA model focuses on understanding the long memory process, which means past observations have a lasting impact on future values of the specific variable we are interested in studying. As a practical example, we are going to carefully examine the time series properties of the KPM beta. For anyone who might not be familiar with the KPM beta, it essentially describes the correlation between how a firm's stock returns fluctuate and the overall market's return fluctuations. So if you were to calculate the return, for example, then you proceed to do the very same thing in relation to the overall market. What we have then is the return of the firm and also the return of the market. The relationship between these two is precisely what we define as the beta. The degree to which a company's financial return is exposed to the overall market's movements will determine its beta value. For example, if the overall market index experienced an upward movement of 1 unit this month, that would signify a corresponding increase of 1 unit in the market's value. But then, what kind of reaction would we observe in a specific individual stock? If that particular stock were to move by 1.5%, it would then imply that this stock possesses a beta coefficient of approximately 1.5.
So, to reiterate, beta fundamentally measures the sensitivity of a company's or an asset's financial returns to overall market movements.
Now, we are going to proceed with applying the ARFIMA process directly to the beta. This is because the beta tends to exhibit a very high degree of persistence over time, which is a critically important characteristic to consider. In this specific situation, the autocorrelation can often prove to be quite significant. The autocorrelation is simply defined as a statistical correlation of a specific value with its own past observations. For example, we might look at the relationship between xt and xt minus k.
So, the augmented reality portion, which is
the first component we're examining, is the ARFIMA model. This ARFIMA model and its structure comprises several key elements. It specifically includes the autoregressive or AR component. It also incorporates a crucial partial differencing aspect, and then it has another important part that completes its overall design. These are the three essential components we must acquire to successfully run the ARFIMA model. The AR part specifically represents the inherent momentum, detailing precisely how the current value of our variable, in this particular instance the beta, is directly affected by its preceding lag. We're examining the beta value from the past, specifically, for example, over the last month. The value observed over the 5-year period serves as the autoregressive coefficient. Should this coefficient be significantly large, it implies that we are experiencing an AR resistance. The other element here is simply something that cannot be explained by the past value of the variable, like unexpected shocks or errors. However, if we believe that the xt can also be affected by various external factors, then our approach might need to be adjusted. The variable's value from 2 time periods in the past, which we might denote as xt minus 2. With this, we achieve an even more powerful and robust autoregressive process. It takes into account not merely the immediately preceding data point, but also the 2 distinct values that occurred prior to that. Furthermore, this analytical framework can be expanded to include 3, 4, or even 5, or indeed many more historical time periods. Now, can the xt minus 2 affect the xt? If we were to include this particular element, it would indeed signify an affirmative, but with a somewhat diminished overall effect. So considering the first lag in our statistical model, for example, let's just assume that the phi coefficient value is precisely 0.5. And for the sake of argument, let's say that when we consider a longer time lag, naturally, the observed effect will diminish. So, in this context, we're looking at the phi coefficient squared. For example, if that were 0.5 squared, the outcome would be 0.25. The reason for this is if we are observing a consistent process of decay over time, a continuous decline, meaning that the phi coefficient remains the same, but the actual reduction occurred exponentially. Consequently, the effect associated with the xt minus 1 variable ought to be substantially more pronounced when compared to the impact observed from the xt minus 2 variable.
So if the effect here is 0.5, then the effect here also will be 0.5 because we have lag 1. Now, considering the effect of x sub t minus 2 on x sub t, we then have a factor of 0.5 for the x share and then another factor of 0.5 applied to each x sub t, which means we are multiplying by 0.5. If this occurs twice, the result will be 0.25. This entire process functions like a chain, so if we consider xt minus 3, the identical process would apply. However, the effect will gradually begin to decay. So what we're seeing here is essentially an exponential decay that occurs over time. This represents an atypical autoregressive process. So in this particular context, how exactly can we go about determining what we refer to as the partial difference? To achieve this, we have the option to thoroughly examine the underlying R process, specifically by carefully analyzing the autocorrelation function or ACF chart. And rest assured, we will be demonstrating precisely how you can accomplish this task effectively. Moving forward, our very next crucial component to consider will be denoted as D, which represents the concept of the partial difference. So the question is, how many times do we actually need to difference this series or apply a partial differencing operation before it's appropriate to then apply the AR process? Pause. Let's consider an example here where we have a specific equation. Pause. For instance, if we make the assumption that the constant C is equal to 1, then the entire equation will simplify down to just 1 divided by K.
Raised to the power of 1 minus 2D.
So if you select the partial difference and make that equal to 0, and then the equation will be transformed into a different form. Or we're looking at the autocorrelation, specifically the raw data. This represents the raw form, meaning it's the direct autocorrelation value. K here indicates the number of lags we're considering. For instance, in this particular example, we currently have 2 lags. All right then, let's consider a really large number. For instance, we could take the value of 100. So what's the autocorrelation between xt and xt minus 100? So if the difference in order represented by the parameter d is to a value of 0, this fundamentally means that we are not performing any difference in operations whatsoever on the raw time series data. In that specific scenario, the P100 component, which is a crucial part of our model, will then become 2, which can also be expressed as 1 divided by k, according to the established mathematical relationship. And that value is precisely equivalent to 1 divided by 100. This results in a very small decimal number, specifically 0.01. However, if we were to set a partial difference parameter to a significantly higher level, this particular adjustment should then clearly indicate that we are observing a much slower rate of decay, or alternatively a higher degree of autocorrelation within our data. For instance, if we consider the variable d
is equal to 0.25,
then the pk,
the equation itself will eventually take on a form that is equivalent to 1 divided by the variable k, which is then elevated to the power of 0.5.
and if we apply a lag of 100 in this context, it means that calculating the autocorrelation between xt and xt minus 100 will result in a value of 0.1. So, it's quite clear that you can easily observe the distinction here. A higher value for D, therefore, suggests that we are experiencing a much slower rate of decay and a significantly more robust memory. Specifically, the memory we are referring to means that even a lag of 100 time steps still manages to significantly influence the current value, thereby confirming that this memory is exceptionally long-lasting. And what occurs, for example, a full 100 years in the distant past will undoubtedly continue to exert a significant and lasting influence on the current value. And for this specific scenario, we require a higher degree of partial differencing. So let's now return to the complete comprehensive model we've been discussing. We've already had a detailed discussion about the AR component, which is the autoregressive part we covered earlier. And furthermore, we also thoroughly discussed and analyzed the D component. Indeed, we have just finished our detailed examination of that specific element right here. The Q component within this model's framework is quite simply defined as the fundamental error term. So the Q variable here specifically relates to the moving average component, which is primarily concerned with handling the MA shocks. This concept is quite similar to the autoregressive part that we're expanding upon. However, instead of using the lagged values of X, we are in this case employing the lagged error terms. Therefore, our approach involves utilizing the historical innovation, specifically the unexplained component within a time series, to elucidate the current magnitude of the particular variable under consideration.
So there are these short-run dynamics at play. Typically, the Q value isn't a very large number, and that's because we're primarily concerned with the error term. This error, by its very nature, is not anticipated to have any lasting long-term impact. However, it certainly could manifest as a short-term effect, and such an effect might well be incorporated into our predictive model. So we're really making an effort to incorporate all potential factors that could influence the XT. This is crucial because our main objective here is to accurately model the time series variables, specifically beta, as it evolves over time by utilizing its own historical data and previous observations. It accounts for the impact of its own previous prediction errors, with the current data undergoing a difference in transformation before the ARMA model is applied.
Before applying AR and MA, we must determine the correct partial differencing to model accurately.
I just want to give you a quick reminder about some of the notation you might see in your textbooks. Specifically, the capital letter L is used to denote what we call the lag operator. So for instance, if you see LXT, this notation simply indicates the value of x at time t minus 1. Similarly, when you encounter L squared xt, it represents the value of x at time t minus 2. And following this pattern, LKXT generally signifies the value of x at time t minus k.
So considering everything, what's the most effective way for us to proceed with the ARFIMA?
We are going to be applying both the autoregressive AR and the moving average May models in our analysis. However, first and foremost, it's important to note that we won't be using the original variable directly. We absolutely must perform a transformation on that data. I meant to indicate with an X that we are not using it in its raw form. So to be clear, we will not be using this. Instead, we will exclusively use the transformed data.
Form.
Let's simply call it Y.
So, the variable yt in this particular context can be expressed as follows.
Set w, or the weight parameter, to 0 and then multiply that result by xt.
Plus.
We need to take the weight of 1 and then multiply it by the lagged value of xt. My mistake.
So for instance, this would represent 2 multiplied by the value of x at time t minus 2, and this pattern would continue. Essentially, what we're looking at here are the historical values or the past observations of our primary variable. Specifically, in the context of our current discussion, these refer to the capitalization and the beta coefficient.
So, how exactly can we find the value of w? The w in this case is determined by the math
of this particular equation.
For example, if d equals 2.4, now we're going to determine these specific weights. W0 naturally is at 1. We always begin with that initial value. Now for W1, if you carefully apply that mathematical equation, you'll find it comes out to be negative 0.4. And then for W2, the value will be and so on.
Once we have the W matrix, we then multiply it by the X variable and its corresponding legs to calculate the YT value. We then repeat this identical process to determine the values for YT minus 1, YT minus 2, and so on.
So, for example, in this situation, if we consider the original variable xt, which represents our beta value, and then we have the current period's observation at 1.2, the lagged value from the previous period at 1.1, the value from the previous 2 periods at 1.005, and so forth.
And then if we were to set the d, that is the partial difference, to a value of 0.4, we would then obtain these particular weights.
And if we proceed to apply the YT equation, the one that I previously outlined and wrote down here, we're essentially going to be multiplying the individual weight by its corresponding beta value, and then we'll take that product and we'll do the same for the next pair, and subsequently we will sum all of those results together.
If you perform the multiplication and then you sum all of those values up, the YT will then be 0.5. However, in this specific scenario, we absolutely require a complete time series. Consequently, we must also acquire the value of YT from the previous period, which is YT minus 1. How can we accomplish this? It's quite simple, really. We'll just start from this particular value. So this specific point will be designated as W0. Yes, W0 is what we'll use as our initial reference point here. So we simply apply a lag to it. We keep the same W value, but we just assign a tag to it, and then we determine the WT from the previous time step, which is WT minus 1. And in a similar manner, we can find the YT values from 2, 3, 4, and 5 steps back. So we now have a completely new transformed series of data. For example, if we were to set d equal to 0.4, just as we did in our particular case, we then successfully identified the values for yt minus 1, and yt minus 2. So this is precisely how the new variable would then look. That earlier one was the original variable. This is the new transformed variable according to the arithmetic method, because the arithmetic's main purpose is simply finding the transformed variable before applying the ARFIMA model, which includes the autoregressive AR and moving average MA components. The partial difference is 0.4, and these are the values we obtained. If we have a time series, for example, you'll notice that we don't fully difference or take the first difference of the variables, and this is why we have some slow-moving trends.
We're looking at a particular decay process. This represents the resulting fractionally differenced series. It's important to note that this is not a totally differenced series, but rather, specifically, a fractionally differenced series.
So, in our current endeavor, we are actively striving to establish and maintain a significant level of persistence. This is absolutely essential for us to successfully retain and fully capture the crucial long memory effect that we observe, because the fundamental idea behind any form of time series modeling is ultimately to effectively identify and then completely remove the inherent non-stationary problem. Standard and frequently utilized approach involves calculating what is known as the first difference. For instance, by applying this first difference operation, our primary goal is to effectively eliminate the inherent non-stationarity present in the data. However, if this process is applied too aggressively or excessively, especially when dealing with higher levels of differencing, such as when d is set to 1, there's a significant risk that we might inadvertently lose valuable information. So, this is the fundamental idea behind arrhythmia. We are not performing a complete or total differencing operation here. Our primary goal is to maintain some inherent resistance or natural decay, while simultaneously ensuring that the stationarity process is fully preserved. Consequently, we deliberately choose not to apply full differencing, but rather we opt for a more nuanced approach of partial differencing.
So, I'd like to go back to what I was saying. And once we have successfully obtained the yt variable, the specific one I demonstrated to you earlier, this particular yt, we then proceed to integrate that data into our established ARFIMA model, which inherently includes a constant term, the autoregressive or AR component that we had previously discussed, and finally the essential error component.
For example, in this particular situation, if we possess these specific types of parameters, we can then accurately model the expected yt, converting it into numerical values. So, the autoregressive component effectively incorporates the previous day's level. If we assume that only one past level is sufficient, then this component adjusts for the last period shock. So, if the value of d is set to be equal to 0, this indicates that your original time series variable does not exhibit any long-term memory effect, which implies that we can then proceed to apply the ARFIMA model directly.
In this scenario, there is no inherent memory. This implies that any past values do not exert any influence or hold any effect on the determination of the current value. However, if you are compelled to apply higher order differencing, this strongly indicates that your system possesses a form of long-term memory. The central idea, once more, is to retain the memory, but then we must ensure that it becomes completely stationary. If you are forced to have d set to a higher value, for instance, very close to 1, this implies that your data exhibits an extremely strong persistence, and such a condition will inevitably result in non-stationarity. Therefore, an extreme value for d clearly indicates the presence of non-stationarity, and in such cases, the standard method of partial differencing begins to lose its effectiveness. Well, the main benefit, or perhaps the fundamental idea, is that we should avoid being too extreme when applying integer differencing, for example, using a full differencing order of 1. Instead, we apply partial differencing, which allows us to achieve stationarity, and simultaneously, we aim to retain a certain degree of persistence or memory within the data itself. Alright, so let's now apply this concept by utilizing the Finance ResearchGate website. From there, we'll proceed to select the time series. Alright, so first we're going to proceed with selecting the monthly frequency for our data analysis, and then, for our specific example, we'll establish a comprehensive sample period that begins in the year 2000 and extends all the way through to the end of 2024. Once those settings are in place, we'll then apply the charts to visualize the data, and finally we'll select our primary variable for this particular study, which is the CAPM beta. After selecting our variable, we then need to choose the specific sample or group for which we intend to measure it. For example, if we're calculating the CAPM beta, will that be for just one particular firm, for an entire industry sector, or perhaps for the broader market as a whole? Let's go with a sector.
And let's, for example, take the technology sector as our primary focus. So we are determining the KPM beta value for each individual frame within this technology sector by calculating the mean of that particular point. And let's consider, for example, we should take the median so that we are less affected by the extreme outliers in the overall cross-section. So, for each and every month, specifically in this particular scenario, we meticulously calculate the median value of beta. This calculation encompasses every single firm operating within the entire technology sector. We then consistently repeat this process, performing it every month as we move forward. Therefore, in this specific instance, what we ultimately obtain is the median beta for the entire technology sector. Now, let's apply this. These are the specific firms that happen to be operating exclusively within the rapidly evolving technology industry.
And we are all set. Everything's ready.
So what we are observing here, this represents the movement within our beta phase. We're going to clearly see that there is a good degree of persistence present, and at the same time, we also have a noticeable trend developing over this period. So if we were to examine, for instance, the stationarity, we can clearly observe that this particular series is not stationary because the results from the augmented Dickey-Fuller test are not statistically significant. Consequently, due to the presence of a clear trend, we also lack a constant mean, which ultimately means that we do not possess the property of stationarity. So are we truly able to proceed and apply these time series models? Whatever we apply and then obtain won't be reliable because of the fundamental issues of non-stationarity and non-stability, which we've already thoroughly discussed in our other videos. The arithmetic is going to solve this complex problem by carefully taking the difference. Not just a simple integer difference, but rather a more nuanced partial difference, especially if we are encountering some kind of persistent long memory effect. We are going to thoroughly investigate and examine this crucial aspect right now, without any further delay. So what we're going to do now is apply the autocorrelation function, or ACF, to visualize and understand the decay process. And as you can clearly observe here, we are experiencing a remarkably slow decay which persists even when we extend our analysis to include as many as 24 lags. The decay process we're observing here is remarkably slow. It will certainly require a considerable amount of time, yet its impact remains quite significant. So even looking back as far as 24 periods, its effect is still very substantial. Now, if you look at the partial autocorrelation function, it's quite evident that only the very first lag is truly significant. The remaining lags, in contrast, appear to be practically insignificant. The partial autocorrelation will effectively control for the influence of intermediate lags. So for example, in this particular instance, after we have carefully controlled for the impact of xt-1, we then observe that there isn't a direct effect originating from xt-2 on xt itself. This identical principle holds true for both lag 3 and also for lag 4. Consequently, the reason that we are seeing significant values here is precisely because these represent truly independent and distinct effects. Of the autocorrelation from xt-2 and xt-3, it's because of that indirect connection that passes through the xt. But if you properly account for this, if you effectively control for this specific variable, then we generally find that there isn't any significant autocorrelation present in the data. There might be a minor exception, perhaps at lag 13, but for the most part we don't see it, because the values are consistently falling within a range that is very close to zero, meaning they are not statistically significant. Now, it is indeed a very effective strategy to carefully construct the first difference variable, and then we can proceed to carefully compare the ACF, the autocorrelation function, with that specific data set. For instance, I could take... We'll begin by selecting the appropriate time series transformation. Our primary objective here is to derive a completely new series from our existing dataset. This new series will specifically represent the first difference of the particular variable that we have carefully selected. So let's go ahead and proceed now to create that new series. Now, when we examine the autocorrelation function, specifically for the difference beta series, we can clearly observe that its influence extends for a much longer duration, and crucially, it no longer demonstrates that characteristic rapid decay over time. This specific data series does not demonstrate a gradual decline or a slow decay in its values when observed across an extended period of time, which inherently indicates that there is no statistically significant autocorrelation remaining within the dataset itself. And this particular outcome is exactly what we would expect to see, given that we have intentionally removed any inherent persistence from the data by performing the operation of taking the first difference. The crucial question now is, can we perform partial differencing and still manage to achieve stationarity and then a good model? Considering this, let's proceed with ARFIMA.
Section.
And then we can proceed to apply the model effectively. Within the classical framework, we find.
Please make sure to scroll all the way down to the very end of the document. Here, we are specifically looking at the ARFIMA model, which is known for its ability to capture long-term memory effects. In this particular analysis, our primary focus is on the target variable, which we have designated as beta. Regarding the autoregressive or AR component, its specific order and structure can be effectively identified and determined through the analysis of the partial autocorrelation function of the original variable. If the autoregressive function, AR, exhibits a slow, gradual decay, while the partial autocorrelation function, PACF, abruptly cuts off or stops immediately, that is precisely how we determine the appropriate order or level of the AR model. In this particular scenario, it strongly suggests that the AR level is indeed 1, primarily because only the very first lag demonstrates statistical significance. Once the first lag has been accounted for, the subsequent second and third lags exhibit no additional effect, which indicates that an AR1 model is quite sufficient. All right. So we'll proceed by scrolling down and then making a selection.
As for the MA component, regarding the error shock,
We observe if the ACF plot cuts off abruptly, while the PACF plot exhibits a more gradual decay pattern, indicating a slow decline. And this is precisely how we determine if we are dealing with MA shocks. So let's revisit this point. Does the autocorrelation function or ACF cut off abruptly? And the clear answer to that question is no. Now, considering the partial autocorrelation function or PACF, does it exhibit a gradual decay? Again, the answer to this particular question is no. Therefore, based on these observations, it appears quite evident that we do not have an MA shock present in our data indicating a value of 0. At best, we might concede that there could be one, but its quantity shouldn't be substantial. So for now, let's begin with none.
We'll set this value to 0. Now let's consider the D term, which stands for partial differencing. How can we accurately determine its appropriate value? It's often most effective to simply allow the system itself to handle its generation.
And determine what the proper D, what that truly should be for you.
So, first, we allow the system to determine the appropriate D value, and once that's established, we can proceed to execute the process. Displayed before us now, we can observe the fractional difference window. This particular setting simply represents the specific number of K periods that are utilized in our calculations to accurately determine the YT value.
for example, in this spot.
So how many lags are we actually using to find the YT? In this example, we're using 4.
To determine the value of YT. Now, if you were to set a considerably large number, then we would have...
We need to clearly identify and understand the specific sample period. For example, if at this point we currently have a value of 4, and let's assume that the entire sample period available to us is just 6, then the question arises, how many distinct YT values can we actually obtain from this? We can get YT, then YT minus 1, and finally YT minus 2. It's not possible for us to reverse our steps now, because we've already committed to using a substantial time frame to determine the yearly YT estimate. Consequently, we can't return and apply an auto-error extended period for YT. If we possess a substantial sample size for our primary variable, it then becomes feasible to incorporate a greater number of K components during the estimation process for YT. Considering our specific situation, we currently have approximately 300 distinct observations available to us. Therefore, I believe that setting K at a value of 100 will be entirely sufficient, especially since we anticipate generating 200 YT values. So if you were to set a value of 100, this would imply that to determine the initial YT, we would first need to utilize that 100. Subsequently, the resulting difference between 300 and 100 would represent the total quantity of YT that we are able to acquire from historical data. Therefore, we would have a total of 200 YT available, and this amount should certainly prove sufficient when we are engaged in modeling the time series data.
Alright, so now everything is perfectly in place and ready. Then, we can proceed to apply the ARFIMA.
The data indicates a value of 0.005 for the low partial differencing, which is significant for our analysis. The AR component is very high level, indicating strong auto-persistence, which we observed from the autocorrelation table. Now, the most important metric, which serves to clearly indicate whether we have successfully accomplished a good job, particularly when it comes to performing or accurately modeling the mean dynamics, is precisely this one.
Let's consider whether we observe any significant autocorrelation within the error term of our model. Upon reviewing the results, we can confidently state that there is no statistically significant autocorrelation present. This conclusion is strongly supported by the p-value, which, as you can see here, is quite large. What this essentially means is that after we have successfully fitted our statistical model, the remaining residual errors do not exhibit any problematic patterns of serial dependence or autocorrelation. Upon initial examination, the original time series data clearly presented a distinct pattern of autocorrelation. This was directly indicated by the presence of a notable autoregressive coefficient within its structure. However, after carefully constructing and applying our statistical model to account for this effect, we can now confidently state that no residual autocorrelation remains.
Here we're looking at a comparison between the actual and the fitted data, and here we see the residual values.
Once that's done, we can then proceed to generate the forecasts right here. So, assuming the model proves to be sufficiently robust and highly successful, and you are completely satisfied with its overall performance, you'll then be able to effectively utilize this tool to accurately predict the future beta value, specifically the beta for the entire technology sector. So, if we were to stop our data collection in the year 2024, we would then be able to generate the beta value, projecting it 1 full year ahead. If we possess the necessary data, for example, extending into 2025, then we would have successfully obtained the forecast for a full 12 months ahead, starting from the very last month available within our current sample estimation. All right. I believe that concludes our session for today. I want to sincerely thank you all for listening.